we're going to look at linear approximation, and more specifically, we're going to look at using local linearity, also known as tangent lines, to approximate function values. And we'll talk about what linear approximation means in a little bit. If you want to print a sheet that I'm going to use for guided notes, you can go to this bit.ly link right here. So let's dive into local linearity and using tangents for approximations. And I'll say let's dive in, but first we're going to talk about concavity very quickly. In AP Calculus, we actually talk about linear approximation or local linearity in this context before we get into the details of concavity. So right now I'm going to give you a very, very rough introduction to what concavity is as it relates to a function, and we will cover this in great detail a lot later. So concavity is a word, it's a way to describe the way a graph bends. Are you bending up or are you bending down? There are two types of concavities. The first one is concave up, and if you're concave up, you are doing that. And if you are concave down, you look like a frown. So up like a cup, down like a frown. And there are certain functions that are always concave up, and these are ones that you should already know, but something like y equals x squared is always concave up. Y equals e to the x. You should know that is always concave up. What are some others? On its domain, the graph of y equals 1 over x squared is always concave up. So there are some functions that are always going to have that bending up shape. And one thing to remember is concave up does not mean you complete the full u. For example, if you think about the graph of e to the x only does that. So it's like the right side of the u. But you don't have to complete both sides. So that is what concave up means, and concave down, I've already shown you what that looks like in functions that are always concave down. The natural log of x is always concave down. Y equals the square root of x is always concave down. And there are some others as well, but that is what concave up and concave down means, and we will use that a little bit later. So let's talk about linear approximation. Now, I probably should change the verbiage that I'm using on this sheet. I say linear approximation uses the tangent line. Technically, the linear approximation itself is the equation of the tangent line. And it's the idea in this section of the AP Calculus curriculum, the idea is that we're going to use the tangent line to approximate function values where that point C is close to the point of tangency. So right here I have this kind of illustrated. I have some function f of x, and then right here I have a point of tangency, and I have a tangent to f of x at x equals 2. So I'm going to call t of x the tangent at x equals 2. Now let's just pretend I want to know what f of 2.1 is. Now 2.1 is very close to f of 2. Right? So if I want to know what f of 2.1 is, well, it could be that it's really difficult to plug into f of x. So it could be that f of x is something really ugly that you just don't want to plug numbers into, especially decimals. It could be that the problem is presented in a way that you don't have an equation to plug in. You may have like a table of values or something like that. And so for some reason we cannot plug into f of x. But if you have the equation of the tangent line, well, tangent lines are always linear. So you could actually write that in slope-intercept form. And so what I could do is I could say f of 2.1 is approximately the same as the tangent value at 2.1. And as long as you stay relatively close to the point of tangency, in this case, the one I have drawn here, you can see that f of 2.1 right here is very, 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 very close to the y-coordinate of the tangent at 2.1. Now, the further away you get, the less accurate these approximation techniques tend to be, but that is the idea behind the linear approximation technique for approximating function values. And let's see, let's keep going. So the linear approximation, okay, here it is. So I thought I talked about it in more detail. So the linear approximation is actually the equation of the tangent line itself. Sometimes you will also see the tangent line called the linearization of the function or the local linearity. So if you see a question that says, what is the linear approximation to f of x at x equals 3? That's the same as saying, what's the equation of the tangent to f of x at x equals 3? Linearization and local linearity are also interchangeable there as well. And then I'm going to bring concavity back into the situation here. when you are doing a linear approximation, when you're using a the tangent line to approximate function values, you're going to be either above or below the actual value. So like this illustration that I have right here, when I plug into that tangent, my tangent is sitting above the curve, which is creating an overestimate. If your tangent is below the curve, then it will produce an underestimate. And so when you're asked if there's an overestimate or an underestimate, the question is really, where does the tangent line lie in relation to the curve? And so we're going to go back to concavity. So if your function is concave up on an interval that contains both the point you are estimating and the tangent line, I'm sorry, C is the tangent point, and A is the estimation point. But as long as you contain both of those in a concave up interval, well, let's think about what concave up looks like. Concave up looks like this. So if I draw a tangent to a concave up function, that tangent, no matter where I'm looking, will always be below the curve, and therefore that tangent line would provide under approximations for the actual function values. So we have to determine, is the function concave up or is the function concave down? Similarly, if your function is concave down, then your tangent will lie above the curve, producing overestimates. And so again, if you want to illustrate that, you can just kind of draw a quick concave down section, draw a tangent line, and you can see that it doesn't matter where I draw a tangent to that curve, that tangent will be above the curve, producing overestimates. And in the next unit, we are going to spend a lot of time talking about how to determine if a function is concave up or concave down. Okay, sorry, I had to take a short break there for a hot second. Okay, so what I was saying, we will eventually learn how to, in detail, determine the concavity of a function that maybe you don't already know. However, for now, since we haven't gotten into the concavity in great detail, I'm only going to ask you about the concavity of functions that you should know already, just basic functions like parabolas, the square root of x, e to the x. Or I'll provide the graph, or I'll just outright tell you the function is concave up on this interval. Is this an overestimate or an underestimate? And so we'll do that. So let's look at a few specific examples. And so here we have a function y equals the square root of x, and I want the linear approximation at x equals 4. Stop! I'm going to do that first. That's asking me for the tangent to f of x at x equals 4, and for every tangent you need a point, which will be my y coordinate at 4. And in this case, I'll be the square root of 4. I think that's 2 today, isn't it? So my point is the ordered pair. 4, 2, and the slope is found by the derivative, so I'm going to find y prime, and the derivative of square root of x is 1 over 2 root x. And then I need to find the slope specifically at 4, whoops, not y prime equals 4, y prime of 4 would be 1 over 2 square root of 4, which ends up being 1/4. And so there's my slope. I'm going to roll those two into a linear equation, y minus 2 equals 1/4 x minus 4. So there is finding the linear approximation. That is the tangent line. Then it says use that to approximate the square root of 4.1. Well, that's basically f of 4.1. And I'm going to go out on a limb and say that y'all don't know the square root of 4.1 off the top of your heads. So if I want to approximate f, and by the way, I'm kind of replacing the y with an f here. If I want to approximate f of 4.1, I guess I'll call it y of 4.1. That would be approximately what I get if I plug 4.1 into my tangent. So that'll be 1/4 of 4.1 minus 4, and I'm going to move that 2 over. Now, if it's a free response question in AP Calculus, you can stop there, but I'm kind of curious. I have 1/4 of 0.1. I'm going to change 1/4 to 0.25. So I have 0.25 times 0.1 plus 2, and that's going to end up being 2.025. Now that's my approximation. That's what the tangent line says the square root of 4.1 is approximately equal to. I'm going to pull up a calculator. Let's see what the square root of 4.1 is. And see, I was doing some work here earlier. I'll just go to Scratchpad to get all that stuff out of the way. So the square root of 4.1 is actually 2.0248. So in a calculator, I determined that the square root of 4.1 is actually equal to 2.0248. And man, if you consider rounding, my linear approximation technique was actually accurate to the 1,000th decimal place. That is impressive. If you want to show off your skills to some people, just random people you may meet on the street, Show them how to do this. That's pretty cool. The square root of 4.1 accurate to the thousandth? Man, that's something else. All right, let's move on. Oh, I forgot. I didn't finish the question. Sorry, without using a calculator to determine if this is an overestimate or an underestimate. Okay, well, I just cheated. I know this is an overestimate because I just punched this in a calculator, and boy, it's just barely an overestimate, but it is an overestimate. Without a calculator, you would need to consider the concavity, and you should know that the graph of the square root of x looks like this. It is concave down. And since f is concave down, since my function is concave down, this is going to be an overestimate because anywhere I draw a tangent will be above the curve. This is an overestimate. My writing is crap because y equals the square root of x is concave down. Cool. Cool. All right, let's go on. I may jump around and skip some of these for the sake of time. I may just talk about them a little bit. Find the linearization of this function at 1. So that's another word for the tangent at x equals 1, and estimate this function value with that. So my tangent, I would need a point. That would be f of 1, which would be 1 plus 3. That's 4. My slope would be f prime of 1. And so this is very much like the previous problem, f prime of 1. I'll start by finding f prime of x, 4x cubed plus 6x. I guess I'll go ahead and finish this. I'm almost done. F prime of 4. Holy cow, this is a big slope. 4 times 4 cubed is 256, plus 6 times 4 is 24. So we get 480? Really? That is a ridiculously steep slope. Holy cow. I'm supposed to plug in 1, not 4. No wonder. Goodness, Paul. That's embarrassing. That's embarrassing. F prime of 1. Oh, well, that's a lot nicer. That's just 10. So now my tangent line is y minus 4 is 10, x minus 1. And then f of 0.99 would be approximately 10 times 0.99 minus 1 plus 4, which would be 3.99. I don't know. I'm not even going to try to clean that up. You can throw that in the calculator. So there's the linearization for number 2 and using that to approximate f of 0.99. And for the sake of time, I'm going to skip 3. It's a little bit of a complicated one, but I want to skip that one. Oh, that will take some time. I may work this one out and put it on the video at the end just to show you the answer for those of you who want to give that one a shot. And I want to jump to number 4. Number 4. So we have a graph of f prime. I want the equation of the line tangent to f at the point 25. I am provided the point. I need the slope. I need the slope. The slope would be f prime of 2, and we're given the graph of f prime. Pay attention to that. At 2, f prime has a y-coordinate of 3. Now, you may be thinking, the derivative does not exist. That's a very slight corner, but this is f prime, and there is clearly a point at 3. So my tangent line is y minus 5 equals 3 times x minus 2. And then f of 1.9, we'll simply plug 1.9 into that. 3 times 1.9 minus 2 plus 5. 3 times negative 0.1 plus 5 is going to be 4.7 is our approximation of f. And I'm going to pause recording. And for those of you who want to attempt this problem, I'm going to work it out, and then I'm just going to put it up on the screen here in a second. All right, so here's my work for number 3 here. It's an implicit differentiation problem. The point 3,1 is lying on this curve. And it says use the line tangent at P. So I need a slope. I already have the point. The slope's going to be a little bit more complicated. So we do the product rule with xy within our implicit differentiation. I distributed my negative and cleaned it up. One gift about this problem is that, remember, if you have an implicit differentiation problem, if you have a point to plug it in as soon as you complete the derivative, because it makes solving for dy dx a lot easier. So when I plugged in 3 for my x's and 1 for my y's, it cleaned up to this. You end up with 5 dy dx, and really there's a plus 5 here, but I went ahead and subtracted that over here. The slope is negative 1, and then once you get that slope, it becomes just like the other problems. go to point slope form for your linear equation. I moved my 1 over and I plugged in to get 0.9. So there's a quick overview of using linear approximations to estimate function values. Hope that made some sense to you.